In this video, I will be discussing the two distributions we can use for modeling p-hat, the sample proportion. First of all, let's talk about what the point is here. Well, I think one of the really important things for students to learn to understand about statistics is that we calculate probabilities, and p-values are one of the really common probability values we use and interpret in statistics. We calculate these things using distributions. So these distributions are really important to understand, and especially it's important to understand if you're using a distribution that's appropriate for the population and things like the sample size and the circumstances surrounding the whatever type of research you're doing. If we're talking about sample proportions, it's really convenient to think first about a model like coin flipping. And most people I find have had some experience flipping coins. The reason coin flipping is a good model for our sample proportion is because it's a binomial situation. In other words, there are two possible outcomes, right, when we start talking about flipping a coin. The outcome can either be a head or it can be a tail, right? So flipping a coin is what we call it's a binomial situation. We could think of the sample proportion as a binomial variable. And when we're talking about a fair coin, well, a fair coin means that the frequency of heads and tails is the same. It's 50-50. Or the probability of flipping a head or flipping a tail is 50%. Now, we're going to make some definitions here as we move through this discussion, because when we start to think about distributions, we have to think about the variable that we're using or we're trying to model. And in this case, the variable is the sample proportion. So we're going to just think about a situation here. We're going to call flipping a head success. In binomial language, or when we're talking about binomial situations and statistics, we usually refer to success and failure. And we could define success as being flipping a tail as well. But we're going to just go ahead and say flipping a head is a success. And if we flip the coin 10 times, then the number of trials or the sample size is 10. And the population proportion value would be 50% because we're assuming that it's a fair coin. And now notice we have our variable. X is the number of successes. And that variable has a sample space. And actually, we call it, in statistics, we call this a random variable, because the values that variable will take on are random events. And the sample space here this is all possible values for X. Or we could think about it as all possible values X could be. Oop, learn to spell could be. There we go. Okay. Now we need to think about p-hat as a variable. Oops. And I want to, first of all, illustrate that the formula for calculating p-hat, this is the number of successes, right? That's our X value. And it's divided by the number of trials. And so, for example, if X turned out to be 5, N is 10, that means we would have had a result of 0.5 here. And what I'm going to do is use the calculator here for a moment and simulate coin flipping on the calculator. You might recall earlier in the semester we were using random integer for things like, simulating coin flips or rolling dice or various other things. Not rand, I want random int. And we're going to use a lower limit of 0 here, upper limit of 1, and we're flipping the coin 10 times. So when I press enter here, I get a sequence of zeros and ones. And in this case, I got 1, 2, 3, 4. And if I define 1 as heads and 0 as tails, then I would say I had 4 successes on this particular simulation of flipping a fair coin 10 times, and the result was 4. And if I do that again, this time I get 1, 2, 3, 4, 5, 6, 7 heads. So p hat in this case is 70%. And see, I'll do that one more time. 1, 2, 3, 4, 5 this time. So notice that when we do the simulations, or when we flip the coin, 10 times, and we repeat that process, the value of p hat is changing, it's varying. And if I continue to do this simulation, or in other words, if I flipped my virtual coin over and over and over again, these x's would start stacking up, and I would start to see, get an idea for what the shape of that distribution might look like. Now, the other thing we can do is we can use mathematics to calculate how frequently each of those outcomes should happen, okay, or each value of the sample space. And that information, that set of possible values for the variable, and the theoretical or the mathematical probabilities or relative frequencies, if you will, with which each of those values occur, that's what the distribution is. And notice this is a screen capture of just my TI calculator. So these are lists in the calculator, and I've actually put the distribution in the calculator. Notice I have the set of all possible x values, 0 through 10. I've converted those to p hats by dividing all of these by 10. And these are the probability values. So that's one way to denote or to represent a distribution, is just as a table. I can also represent the distribution as a graph. So notice these are the probability values. I have this coordinate system set up where I have the possible values for p hat along the horizontal, and then I have these percentage values along the vertical, which are going to represent my probabilities. And notice in this very first case, the probability of getting no heads, well, that's scientific notation. So let me just do a little note down here. 9.8 e negative 4 is equal to 9.8 times 10 to the negative 4. That's scientific notation. That's 0.00098. So that's like way less than 1%. So this first bar on my distribution is going to be really short. The next one is about 1%. So the probability of flipping 1 out of 10 heads is about 1%. And it can carry on here just using the values from the table to determine how high each or how tall each of these bars needs to be. And this is a sketch, so doing the best I can here, but it doesn't necessarily need to be exactly perfect. All right. So again, I could represent the distribution graphically as well as like a relative frequency type graph. And then the other way I can actually represent this distribution is as a function. I can say, well, p of x is going to equal, and this is, I'm just writing this down to show you the fanciness that we can have here. And this is a simpler case of the formula, but this is the binomial formula. And in fact, more generally, when we're just dealing with n and p-values that are other than, or population proportions that are other than 50%, there's a more general form of the binomial formula as well. Sorry, wrote it down wrong. And we didn't spend a whole lot of time in this class talking about things like combinations and such. I mean, we did that a little bit in the beginning, but this would be in combinations of x things, or in things taken x at a time. In choose x is how we refer to it. This would be p, and actually I don't need this parenthesis here. Let me get rid of that. Do that. Okay. Use some implied multiplication here. So this is p to the x times 1 minus p to the n minus x. So that's actually the full-blown version of the binomial formula. This is also built into the calculator. So these distributions are built right in. And this would be binomial PDF on the calculator. And the syntax is in, comma, p, comma, the x value. And that's actually how I calculated all these probability values, is using the binomial PDF on my calculator. And that's why I need the x values. The x values give me the probabilities, and then I convert the x values to p hats to see what p hats distribution would be. Now, we're going to transition into talking about the normal distribution, or the normal approximation of these binomial probabilities. And in the process of looking at that, we need to think about the difference between discrete and continuous. Discrete means that there are the sample space for the variable is either finite or it's countable. It's what we say, it's countable. It could be infinite but countable. It turns out in the case of binomials, the sample spaces are discrete. And that's because we're going to have a fixed number of trials. So if we only have 10 trials, if we flip the coin 10 times, that's our model, we're only going to have 11 possibilities. If we flip the coin 100 times, we have 101 possibilities. So since n is a fixed value for the number of trials, the variable p hat is always going to be actually a finite variable instead of a discrete and countably infinite variable. There are some discrete distributions and statistics that are not finite variables like this, but in any case, this one we're talking about is. And the problem is normal distributions are what we refer to as continuous. So I'm calling the variables as uncountably infinite, and what I mean by that is the set of sample space, or the set of possible values, is uncountably infinite, but the other word we use in mathematics is continuous. And that means the set of possibilities are on a continuum. There are infinitely many possibilities between any two numbers. Let me talk about that on a graph here a little bit. I'm using a histogram to represent the distribution. Notice this has the same basic shape as the stick diagram I drew earlier, frequency plot. And one of the issues we have with histograms is that, if you recall, the bin, or the range of values here, it represents all possibilities between 0.5 and 0.6. And so, like, for example, technically, the x value here could be like 5.5 or 5.73 or etc. So all of these numbers are real numbers, are represented by the histogram. But we're modifying our usage here a little bit because each of the left-hand values represents the actual bar itself. So this would be the 0.5 bar, and notice it's about 25% of the time we're getting 0.5. So I've kind of modified this histogram to fit the situation with the binomial variable p hat. And I should actually put p hat on my axis here too to notate that. Well, since really we're representing in each one of these intervals, I'll use some interval notation from algebra, but if you remember, these are half open intervals. So when you were graphing these in algebra, you would have done like graphs where you have, one steps to another steps, another interval wise. And so they represent that whole range of values. Now, the normal curve, when we think about a normal curve, the height of those curves are not probability values. It's the area under the curve that we interpret as probabilities. So in order to do an analogy where I'm talking about a histogram for a binomial distribution, representing something similar to a normal distribution, I have to think in terms of areas. And so what I need to do is I need to do a rescaling. And this is so the calculator, I made these graphs, by the way, using the TI calculator. I just did screen captures of the screen of my virtual TI, and that's where these graphs came from. So in order to get the normal curve to fit on the graph of a histogram for the binomial distribution, I have to do a rescaling of this axis, basically, or of the heights. So instead of the height being the area, the actual, or the probability, it's actually the area of the bar. And I wanted to show you, now when I do this kind of work, I have a tendency to use, to draw a graph and to think through what I need to do. And so I need to think about, how do I rescale so that instead of the height being the probability, it's the area. And so I want to think about, well, okay, these are rectangles, and so the formula for area is base times height. I know the class width here is 0.1, the way I set up my histogram. And so if I want the area to be the probability, I know this is getting confusing probably. If I want the area to be the probability, then I need to multiply all the heights by something so that the actual height is the area. And so since this is like 1/10 times h, I see that if or that's not b, times h, yeah. I can see that, well, if I want to make the area now the probability, I need to multiply this by 10. So I need to multiply all of the height data by 10. And that's why I'm going to go back a couple slides. That's why you also see this bar, or this other list in my calculator that's just HT for height. So I multiplied, I rescaled the graphs in such a way that, and actually this is a different one. This was for a different example, I think. But in any case, but that's why I have this height list, is when I go now and I multiply all those heights by 10, I now have a histogram that I can compare to what the normal distribution would look like. And for both of these are centered at 0.5. So the histogram is representing the binomial, which we notate as BIN for binomial, and then the sample size and the probability of success, which in this case is 0.5. And the normal distribution, okay, which is this blue curve. I'll get fancy here. I'll switch my pen color, over to blue. And so the normal curve, the distribution we're using here is normal. That's where what the n means. Centered at 0.5 with a standard deviation of 0.25 divided by 10. And again, my video here, this video is not to talk about all the different formulas and things like that, but just to show the two different distributions and how they're different and how they're used. So now notice that one of the things that we have to keep in mind is for the normal distribution, we calculate probabilities based on areas. So for example, if I was going to calculate the probability of like 70% heads, well, that would just be the area of this bar right here, right, for the binomial. But for the normal calculation, I'd have to find the area from actually 0.7 to 0.8, which would be, I've got to switch colors now. Hold on here. And actually, I think what I want to do is, let me just erase this and just focus on blue for this area down here. So that would be the area. So the approximation that we would get from the normal distribution would be the area under the curve here. And notice that. And generally speaking, we wouldn't, when we're using a normal distribution here in this way, we wouldn't talk about the probability p hat is equal to 0.7. Let me put my variable on the axis here. We'd really be talking about the probability that p hat is at least 0.7, because that's the kind of the language we use when we're talking about p-values and things like that. And so that would actually mean that we're shading that whole tail area. And so what you should see here, what I would like you to notice, is that there's a discrepancy here. There's an error between the estimate that we would get using the normal curve or the normal distribution versus the binomial distribution, right? Because all of these corners here that are getting cut off by the normal curve, that's all error between the two estimates. So we call it a normal approximation because it's not going to give the exact value. It's going to give an estimate. So what ends up happening is as the sample size increases, so this example I'm using n as 20, the same p-value, which is 0.5. Again, we're talking about flipping fair coins. That's our model. And notice that now I've doubled the number of rectangles by increasing the number of trials or doubling that. And so now we're going from 0.5, still the center point, but this would be 5.55 and 0.6 and 0.65 and 0.45 and 0.4 and so on. And notice now, if we're talking about the area from 0.7, the same probability p hat is, say, at least 70%. Now we would be talking about the area under the same, essentially the same area under the curve, or it's sort of like that. It's not exactly like that, but we would start at 0.7 and we would, this area under the curve, and notice we're reducing the error. And I have one more example here. Here I have made n equal to 100, and p is again still 0.5. And notice, there's a point here, there's a threshold where really the curve, the probability of these numbers are basically zero, and basically zero here. And so I think that this is about from 0.3 to 0.7 is where we actually see some relatively large enough probabilities that make them worth considering. So I truncated, I chopped the graph off just to focus in on that range of values. And you can see again, we're reducing the error. So as the sample size or the number of trials increases, the error between the two approximations goes down. Or I'm sorry, between the normal approximation and the actual binomial probabilities, that error gets smaller and smaller as the sample size goes up. And notice I wrote here the sample size requirements for using the normal distribution to approximate these binomial probabilities. It's n times p is at least 5 and 1 minus p times n. Ooh, I didn't write the n. Let me put that in there. N times 1 minus p and n times p. And again, here I did a screen capture of finding the area here on the calculator. And just to show you that shaded region there. The other thing that can happen when we're modeling these binomial probabilities is that the proportion or the parameter value, the population proportion, can be something different than 0.5. And in this case, I drew an example where we're talking about a sample proportion or a population proportion that's 70%. And what that does is it gives a skewedness to the shape of this distribution. And you can see here the normal curve's really not going to fit this very well. And in this case, notice that n times p is 7, because p is 0.7, but n times 1 minus p is only 3. So this would be a situation where we would need a sample larger than 10 to use a normal approximation. So when we have a skewed kind of binomial distribution like this, we'll need larger sample sizes. And again, I've superimposed what the normal curve would look like, and you can see there's just too much error here to say that the normal curve is going to do a very good job in this particular situation. I want to work through an example. And again, this idea of a coin flip, as our model for binomial, it can be applied to so many situations. And in this example, I have a statue here of President McKinley, William McKinley, and this is the statue that used to be on the plaza in Arcata, California, and it was removed. And it was removed because President McKinley was an imperialist, and there were a lot of issues about his what he stood for. That the city council especially felt like we should no longer be represented in this way. But the issue was controversial, and so I'm using this as an example because one of the things that the city might have decided to do, the city council, is they might have thought, well, what do the majority of the Arcadians think, the people that live in Arcadia? And so they might have done a survey. The question might be, we're making an assertion the majority want it removed. That's the belief, perhaps. And so we could think about that in a statistical hypothesis, where the alternate assumption here is the majority want it removed, which means that population parameter. And maybe I'll define that over here, just to be really clear. Whoops. In this context, what we're saying is that the parameter value, P, is equal to the true proportion Arcadians, the true proportion of Arcadians who want the statue removed. That's our proportion, or our population parameter, our population proportion. So in the alternate, we're saying it's the majority, it's greater than 50%. In the null, we're saying it's not the majority. And so we're going to try to figure out which of these is the most likely true. So we may design a survey. In that survey design, we are going to randomly select 100 Arcadians and ask them this question, ask their opinion. And we're going to give them a yes or no response. Should this statue be removed? Yes or no? Oh my goodness, I noticed I misspelled statue here. That's funny. Oh well. Typo. Two possible distributions we could use. We could use a binomial distribution, or we could use a normal distribution. So in the binomial case, we're going to think about... actually, we're not quite there yet. Well, in the binomial, let me move ahead a little bit. Hold on here. All right, so let's look at this picture. So the binomial case is going to be red-colored rectangles here representing the probability values. And in the normal situation, it's going to be the area under the curve. So what we're going to do is we're going to do a survey. We're going to get a sample, and we're going to use that sample to... calculate a p-value, and we can either use the sum of the areas of these rectangles or sum up those binomial probabilities, or we can estimate the p-value by using the area under the curve. And if we use the normal curve, then we're going to have error in our estimates because we won't be accounting for these upper parts. And again, the direction of extreme here is one-sided to the right. That's why I'm focused on the right tail. Now, one of the questions we got to answer here or think about is, what are the chances of making an error? And specifically, we focus on type 1 error. And, I'm not going to try to write a list of consequences here. A type 1 error would mean that we conclude the majority of Arcadians want the statue removed, and it's actually true that less than a majority want the statue removed. And so... there are a lot of different, we could imagine a lot of different possible consequences. And though thinking about those consequences would inform our decision about what alpha should be. And, traditionally, or common alpha is 5%. This comes from Ronald Fisher and his idea of how rare and unusual data needs to be in order to conclude that it's statistically significant. So we conducted our survey. We got 64 yeses, 38 nos. So what does this mean? Well, ultimately what we're going to do is calculate a p-value. That's kind of like the standard way of determining whether or not our data is significant. What's p hat? P hat is 64%. That's 64 divided by 100. So I want to think about how rare and unusual is this sample value if H naught is true. That's the definition of a p-value. That's what I'm going to calculate. That's what I want to know. And there's a couple of ways I can calculate this. One way is using a binomial distribution. And remember, the binomial distribution is built into the calculator. So, and the feature we're going to use is CDF. CDF stands for cumulative density function. So this is going to be accumulate. What I'm thinking about is it's adding the areas up of the rectangles from the left to the right. CDF, this function on the calculator, it's based on percentiles, so it always adds probabilities from left to right. Population proportion value is 0.5, and then the x value, in this case, we would use the x value for the binomial, which is I wrote the wrong thing here. Let me review this. So one of the tricky things about doing this calculation here is we have to make sure that we get the right number in here. And the 1 minus part is really the complement rule. And so what's happening here is, as we're moving along the p-hat axis, right, we start at 0, but then we get down to like 0.63, 0.64, and 0.65, and etc., and all the way up to 1. And what we're interested in is all of the x value or the p-hat values to the right here, right? All the way to the right. Now, CDF, the CDF function adds up the probabilities from left to right. So if I use 0.6 or 64 here, that shouldn't be 0.64, it's an x value. If I use 64, okay, I'm going to subtract off the 0.64 that I need. So again, this is extremely confusing, I know, but I need to be correct here, I need a 0.63. And so I would go to the calculator and this would be 1 minus, second vars for distribution. 1 minus binom CDF. And notice there's a PDF and CDF. The PDF gives individual probability values. The CDF gives cumulative probability values. And that's what I want. So we have 100 trials. 0.5 is our hypothesized population value. 63 is 1 less than 64, which is what we want. And so the p-value I'm getting here is about 0.0033. Now, this I like to think of as, this is not the estimated p-value. This is the actual p-value. I'll just stick with red ink. I wasn't going to. But so it's about 0.0033, right? Now, the other way that we could calculate this p-value, and again, if I go back and I look at my graph here when n is equal to 100, I could also use this area under the curve. And here I don't have the correct probability value because this is going from 60% to the right, not 64%. So and notice though that I'm underestimating with the normal curve, right? Because it's slicing off these upper right-hand corners of the histogram bars. So the actual p-value is bigger than the estimated p-value I'm going to get from the normal curve here. And it turns out, actually, I think that well, let's see what happens. So I'm going to go ahead and do the same calculation using the normal distribution now on the calculator. And actually, I'm going to go ahead and, well, first of all, let me go ahead and use the normal distribution. So normal CDF is how we would do this calculation. Or I picked PDF on accident. I went CDF. Let me try that again here. So normal CDF. And we need a lower limit. That's a left-hand limit value. We're going to go from 0.64. And again, I can use 0.64 with the normal distribution because it's modeling a continuous variable. And this is where I would use E99 for a really large upper limit. The mean is going to be 0.5. And sigma is going to be the square root of 0.25 divided by 100. And notice the p-value that I would get from the normal distribution would be about, well, they're both about 0.3%. So they're actually pretty close. And that's because the sample size here is large. Or the number, yeah, the sample size here is large. So that means that the normal approximation is going to be pretty close to the one we would get if we actually used p-hat's natural distribution, which is binomial. And there's one more thing I wanted to show you. And saving the best for last, maybe, I don't know. But it turns out that we can also do the same calculation, okay, or the calculator will do this calculation for us automatically. I'm not sure why that's there. Oh, okay. Let me get rid of that. Okay, so it's looking for kind of like a blank screen here to do. I think that's where I want to be. All right, so now we can use something, a built-in hypothesis test on the calculator. It's called one prop z interval. One prop, or z test, sorry. One prop z test. And what the calculator is going to do, and this is on the TI calculator. Now, the reason it's called a one prop z test is because we're going to use a z transformation. And if you might look in chapter 9, you'll find this formula. Sometimes sometimes they'll like put a p sub 0 here, I think, for that hypothesized proportion. In this case, it would be 0.5 minus p hat divided by, actually I have that backwards, I think. Whoops, hold on. And put zeros on these two, I suppose. And in this case, this would be p hat minus 0.5 divided by square root of 0.25. If you do all of these calculations, divided by 100. And that will give a z-score. And then we can use the standard normal distribution since we transformed our random variable from p hat, or from p hat to z, and use it. Well, this is built into the calculator. Let me show you how easy this is on the calculator. So on the calculator, to get this exact same p-value, the approximate p-value using the normal distribution, what we do is we go to stat, go to tests, and we choose one proportion z test, number 5. And it's going to ask me some questions. What's P naught? That's 0.5. What's X? That was 64. And what is N? That is 100. And what's our alternate hypothesis? That the majority believe, so it's greater than 0. And we can either do draw or calculate. I'm going to do calculate. And notice I'm getting basically the same p-value. Sometimes there can be a little bit of round-off error here. I don't remember what I got previously. I didn't write down that much accuracy, but it's pretty close. But in any case, yes. So here it is. There's the p-value. It's about 2.3% roughly. That's a pretty small p-value, so I would be comfortable concluding that the majority of people in Arcata definitely wanted this statue removed. But again, it could be just that we were unlucky and we got an extreme, set of opinions or something in our sample. So I hope this demonstration helped clarify the differences between those two distributions and why the binomial distribution we could consider p-hat's like exact distribution or its actual distribution, where the normal distribution is used to calculate binomials. And when we use those calculations, we end up with errors because of the difference between the nature of the two distributions, one being discrete and one being continuous. Okay, well, as always, please feel free to send me messages if you have any questions. This is important because it is a possible final exam question for the course. So again, please feel free to message me questions, and I'll see you next time.